So this is the game that I made. It's called Voronoided, and as Billy pointed out in the chat, it's a pun based on a song by Death Grips. The noided part is the lyric, but yeah. So this is the game. You are kind of a polygon with eyes, with googly eyes. Let's see.
I think
Right.
you should
So,
eat food,
oh.
get bigger.
Okay, yeah. So we'll talk about that in the coding portion. Uh, but yes, that is where we're headed. So some things to notice, I guess, is that players, we can't overlap, but we can uh, our position to each other influences the other person's shape. And so, okay, if you go into at the top of your screen, you should see a button called debug. If you click on that, you'll see some points. And if you move around, it starts to make a little bit more sense of the logic behind how your character's shape is determined. And so if you get really close to one point and then circle around it, it becomes a quite clear actually that there's like a hard line between you and the points around you. Okay, so these are just some observations that we can make, and so now we'll get into what's actually behind the magic. All right, so I'm going to share a presentation on my screen. So today we'll be talking about, or we'll be sort of investigating what are called Voronoi diagrams. And so that's the Voronoided title. That's where that comes from. And so to be clear, this is more of an investigation than it is a lecture. So this project for me came together over the course of a weekend, and I treated it more as a game developer hacking a thing together than I did as a mathematician trying to rigorously understand something. So the contents of this won't be, well, yeah, it won't be that rigorous, but we'll look at some cool pictures. So we just played a bit of the game. Next, we're going to learn a little bit about Voronoi diagrams. We'll discuss a brute force algorithm that I wrote, which I use in the game, and then we'll add a new feature to the game. Right, oh, we just did that. Okay, so this is what's behind what's actually happening. This is called a Voronoi diagram, and there's a few parts to this. So the first part is the points. So the points we call sites, and what's surrounding the sites we call cells. So each polygon, that's a cell. A cell goes around a site. And what's special about a cell is that a cell is composed of all of the points in the plane which are nearest to the site. So if we look at just this blue one in particular, everything in blue is nearest to that red point in the center. Something else to notice about this diagram is that the dashed lines on the edge of the cell. So what that indicates is that the actual lines, the edges themselves, are not included in the cell, because those lines, those points on the lines, are actually nearest to multiple sites. So an edge is nearest to two sites. If we look at where multiple edges intersect, like I think everything here intersects, we only have three edges intersect. Yeah, so in some places there are points that are nearest to two sites, in other places there are points that are nearest to three sites. And so we don't include those in the cells, and I've just termed those the net, but we may also call those edges.
Hey, Ethan.
Yeah.
Do you want us to see your cursor? I'm not sure if you were pointing out anything, but we can't see your cursor.
Oh, no, I wasn't.
Oh, okay. Sorry.
But yeah, maybe I will now. All right, so these are what we're dealing with. We have the sites, cells, and then the things that are not in the cells, which are a net. And so together, if you take all the cells in the net, they form a partition of the plane. So this is cool, but we can also do more. So there's no reason that our sites have to be a point. We can also use sites that are lines. And so in this case, the black objects, those are the sites, and then the gray are the edges. And then in this example, we're using curved lines and points for our sites. And here, our sites are polygons. We can also mess with the dimension. So this is an up-dimensionalized version of what we were just looking at in 2D, now in 3D, where our sites are points. And in addition to that, we can also mess with the distance metric. So what I mean is what I had said earlier, that a cell is all of the points which are nearest to a particular site. And so that when I say nearest, that involves a distance measurement. And so we can change how we measure that distance. So we've been looking at Euclidean distance as one that we're all pretty well acquainted with, but we can use other distances. And so the one on the right goes by many names: Manhattan distance, taxi cab, L1 norm. And so it gives you, it gives you what you see there, kind of diagonals and straight lines. And then here's another cool one. So this one on the left, we have Euclidean and Manhattan again. And then the one on the right, we get some curvy lines using Minkowski distance, which is a generalization of the regular Euclidean distance. So these are the three parameters that you can mess with in your Voronoi diagrams: the shape of the sites, the dimension, and the distance metric. And so some applications of Voronoi diagrams, in addition to just having cool Roblox characters, is geometry. So this is the one that I was familiar with when I tackled this, was nearest neighbor queries. And it's, so if I go back, it's, so a nearest neighbor query is if we have a set of points like we do with these black points on the left, we want to know, given a point on the plane, which is the nearest black point. It's a nearest neighbor query. And it's kind of just a direct application of the Voronoi diagram. So if we say pick a point in the pink polygon and we ask what's its nearest neighbor, well, it's going to be the site that's in the pink polygon. It's kind of like constructed for this purpose of nearest neighbor queries.
How is the region defined? Like if you were to actually do that, you've got your point, you've got your Voronoi diagram. How do you identify the region?
So the way I do it is a region is defined by the edges around the cell. And so if you consider that to be a polygon, then you can do a point and polygon check. So you, yeah. So that's one application. Here's some more I just pulled off Wikipedia. I thought one that was kind of funny to me. So the last one for robot navigation is kind of the opposite of a nearest neighbor query, where points are obstacles that you want to avoid, and then the edges around the cells are the safest paths to take because they're furthest from the obstacles. Okay, so that brings us to Voronoided again, and okay,
Yeah, I've heard about the robotics application, and specifically with respect to like if you have some kind of robotic arm on a bunch of axes and you want to move through some complicated 3D space, or there's constraints, like instead of say there's physical objects in the space that you're trying to avoid, it's more like there's sort of limits to how far you can like rotate on a certain joint before you intersect yourself or something. And so you might be doing some very complicated like articulation of the arm in order to get something from one configuration to another, and you want to find a safe path through that.
okay. just thinking about how that might work is daunting. That sounds like a very hard problem to solve. Right. So Voronoided. So if we go back to the game, now we understand that your character is at the center. We have a white dot, and my character, that's the site, and my character is the cell around the site. That's the end of that. So the way that this game came about is, so it came about from a pun, actually. So now it's called Voronoided, but it used to be called Voronois. And the idea was I wanted to do some like audio visual experience, but I couldn't really think of like how to do that. And so I was talking with Billy, and he showed me this this site. Where is it? Yeah, so I was playing around with this site where it lets you add points to a Voronoi diagram. And I noticed that like when you add a point, it kind of looks like some alien creature moving around. And so that was the inspiration for the Roblox game, is that I wanted your character to be a cell in a Voronoi diagram. And so when you usually do Voronoi diagrams, there's a very common algorithm, at least for using points as your sites and using Euclidean distance. There's a common algorithm called Fortune's algorithm, which is, I suppose, is a quick algorithm. But at the time, I wanted to get this done over a weekend, and so I figured I didn't have time to learn the whole algorithm and implement it. So I figured, well, if I only need the cell for one character, maybe I could write a simpler algorithm, because Fortune's algorithm computes the entire Voronoi diagram, but I only need the cells for individual characters. And so I came up with a brute force diagram brute force algorithm that I hoped would be better than Fortune's for this particular case, but it turned out to just be a lot slower. But I'll go through how it works. Right. So the algorithm I came up with is for a single cell diagram using Euclidean distance. It's a brute force, and it only works in 2D. So a very, very specific case. But it does work, and so I'll explain how it works. So let's suppose that these black points are the world points, and then this blue point will be your character's point. And then also we'll have we'll also have some boundaries, this bounding box around it. And so if you play Voronoided, you'll actually eventually, if you walk far enough, you'll hit a wall. And so that's what these boundaries are. And so also these have vertices too. So we're going to begin with this bounding box as our cell. So we take this box to be the cell, and then we're going to improve on it. And the way we improve on it is like this. We're first going to look at the nearest neighbor for, oh, sorry, something is hitting my screen. We're going to look at the nearest neighbor for our character. And so that's going to be the nearest neighbor. And then we'll draw the line that bisects it. So the reason we do this is that if we just take any 2 points in space and we do if we do a diagram just for these 2 points, we're going to get an edge between them. And so this is just a product of Euclidean distance, really. And that's why this algorithm only works for Euclidean distance. It's kind of by construction only for your Euclidean distance. Right. Okay. So we find this bisecting line between our character's point and the nearest neighbor, and then we look at where this line intersects our existing edges. And we have these 2 points. And then the next thing we do is we're going to draw a ray from our character to these points. So we have a ray in this direction, and we're going to have a ray in that direction towards the other point. And we're going to look at where this ray intersects these are our existing edges. And right, so if this ray intersects our new vertice before it intersects our existing edges, then we know that this bisecting line is going to improve on our our cell. I don't think that made much sense, so let me actually show you a different case. So I'm going to speed run this. So we have this bisector, this bisector, this bisector. Okay, and now let's add another one. And let's see, this is going to be, that's not great. Yeah, that's a bit better. Okay, so this is going to be its bisecting line, and it intersects the existing lines here and here. Then we draw our rays in the direction of these intersections. Well, actually, I suppose that there'd be some more intersections. So there'd be like one up here. There'd be one down here. Yeah, and we look at where we extend these rays, and we see that the rays intersect the existing lines here and here before they intersect the new intersections. And so because of that, we know that our pink bisector will not improve the cell. I hope that made any sense.
I think it makes sense that you could imagine overlaying all the bisections over the Voronoi diagram, and then the region is just like the closest bisections that you can see looking outward.
That's a great way to put it. This algorithm is just kind of an iterative way of doing that. Okay, so let me step back. Right. So that's how we determine with the whole ray thing, that's how we determine if a new bisector is even a valid one that we want to add. And so once we've determined that we want to add this to our cell, now we have to shrink our cell somehow. And what I mean by that is that we want to get rid of these parts here. This was a tricky problem to solve. The way I did it, again, relies on the fact that we're using Euclidean distance. And the way it relies on it this time is that the Euclidean cell is always going to be convex. So if I were to just take any old lines like this and I layer them on top of each other, this inner portion is always going to be convex. And a way to see this is, let's suppose that purple shape wasn't convex. So it looks something like this. And the reason it's not convex is because I can take like 2 points here and here and draw a straight line between them. The straight line goes outside of the shape. So that's why it's not convex. But a shape like this wouldn't make sense because this line here should continue on. And this line here should continue on. So at least that's, in my mind, how I justify why this shape here should be convex. And so knowing that it's convex, what it lets us do is it lets us order our points. It gives us an ordering of our points. And so I order these vertices. I order them counterclockwise. And the way I add the new bisector is that I look through each of these. So I go counterclockwise, and so I look at this point, I look at this point, I look at this point, and I see, oh, so this point shares this edge with the new vertex. So I see that it shares a new edge. So now instead of connecting this top right vertex to the top left vertex, I now connect it to the new vertex, this red one. And then I do this again. So first I find I don't know how to say that. Like the first vertex going around counterclockwise, and then I find the next one, which shares an edge with this second point here. And the data structure that backs this is a doubly linked list. So the vertices are connected in a doubly linked list counterclockwise, and then I throw out the vertices which we can no longer access. Right, I think that covers all of it. So for each of the neighbors, we find the nearest neighbor, we get the bisecting line, we find where the bisecting line intersects the existing edges, and we determine if the bisecting line will even improve on our cell. If it doesn't improve on our cell, then we shrink the cell. Okay. Yeah, I think we'll leave it there for this algorithm. And we'll now get into adding a new feature. Are there any questions on anything I've said so far?
Once you find a bisection that doesn't improve, can you like stop, or do you have to check like the next nearest neighbors? Because you're doing this in order of like what the nearest points are to the target point, right?
Yeah, you're right. So there is an early exit, and so the early exit is if we have right. So if this is our shape, and then we go to add some new vertex with some new bisector, we're going to find the shortest distance from our character's site to the new vertex. And so that's just going to be halfway between them here. And we check this distance. So we compare this distance to all of the distances of the existing vertices. Or no, not the, no, that's right. Yeah. So if, right, this is horrible. Okay, so if the pink distance is longer than all the orange distances, then we're done.
Right, yeah.
Okay. So now I'll explain the feature that I want to add. So Dan earlier had said I should add like being able to eat something to grow, and this is what like everybody has told me to do, and they've compared the game to Agario. So let me hop into Agario real quick. So in Agario, you play as this blob, and you have to eat other blobs to grow. So if I walk into this guy, he'll eat me up, and then he grows. This is what everybody has been telling me to do. Now there are 3 immediate issues with this, or is it 2 or 3? Okay, so the first one is in Agario, you need to be able to run into other players to like consume them. And in Voronoided, by using the Voronoi diagram, players can't intersect, so you can't consume another player. The second issue with this is that in Agario, you collect these dots, or you consume other players to grow in size. And determining or specifying a size of a cell in a Voronoi diagram is not it's not immediate. It's the size of the cell of a Voronoi diagram is implicit. So it's based on what happened there. It's based on all the positions of the other sites, and so you can't just assign a size to a cell. And so that's what I want to tackle today, is how we can get around this and in some sense expand or determine loosely the size of of a cell. So yeah, I guess I'll switch back to my tablet. So I haven't planned any of this out, but I'll go through what my thinking is. And I'd like to hear other opinions too. So we'll suppose that that's my character, and these are the points around me. And so if I want to grow my cell size, what I need to do is I need to push these points away. Or if I wanted to shrink it, then I need to bring them in closer. And what I think a good way to do this would be to have every character's size be decided by a repulsive force. So every character, based on its proximity, has a force that acts on the points. And so if I'm really close to a point, then I'm going to have a high force and push it away a lot. And if I'm far away, it's not going to, I'm going to push it away a little bit. And then also, if my size is greater, then I should also push it away a lot. So I figure we do this. So first we loop over each character, and then we loop over each site. And we need to do some sort of average of like of these repulsive forces to determine the end position of the sites. So I might push it this way, somebody else might push it this way, and that way, and that way, and so we need to do some sort of average there.
You also want a restoring force, like a spring, to pull it back to some fixed position, I guess, right? Otherwise it'll just fly off.
Yeah, so maybe force isn't, okay, you're right. So what you're suggesting is like what I had originally thought of, like putting a point on a spring and like, yeah, simulating actual forces. What I realized is that it's so if we have to simulate actual forces, then we're coding a physics simulation that evolves over time. And
yeah, it'll also be kind of nausea-inducing because your boundaries will be wobbling all the time and stuff.
Yeah, that is one issue.
Didn't you look into like weighted Voronoi algorithms?
I think my research into that was as much as just like, oh, here's an algorithm. I don't actually know how that works.
Right, but like my sense of it was that like each point is associated with a weight, so that if you it kind of just like biases the instead of having a bisection that goes halfway between the 2 points, you have like if if um if one point has double the weight of another point, then like it sort of the bisection line sort of appears more like 3/4 towards the weaker point. If you get what I mean.
Yeah, that's an interesting idea. So like if this has a weight of 4 and I have a weight of 1, then the bisection line is going to be biased towards there.
Yeah, I suppose that would make sense. Yeah. Oh wait, no, but like more the other way around, because we want the like bigger number should mean that you're the
Oh, yeah, you're right.
bigger, so it would be like the blue line is yeah. Okay.
I think, okay, I do like that. The issue I see with this is that the maximum size that a character can be is now this. So we've restricted your character's size.
Yeah. Could you start with a more sparse arrangement of points and a very low weight or something? Like just increasing that maximum size?
Yeah.
Um,
I mean, we're still running into the issue of like at some point there's a cap on how large your character can be.
Right, but to remove that cap, we need to be able to like move these points like to some unlimited amount of movement. I guess something else I wanted to say is like this seems like an interesting problem, starting with this sort of concept of like a Voronoi diagram and trying to derive like an interesting game mechanic and a game to play out of it. And in that, like, maybe trying to derive like Agario like won't result in the most interesting game, like, because then I don't know, you could just go play Agario and it'd probably be like it would a bit simpler. It probably makes more sense for that exact like growing mechanic. I was sort of hoping we'd like find just like we started with this sort of demo of like you just moving around the space, and I was sort of just trying to come up with an interesting game mechanic that arises naturally out of Voronoi diagrams.
What about Voronoi Tron?
What does that mean?
Well, Tron is this light bike game, right, where you control the direction of a line and you try and trap the other player into running into your line. So, it's like Snake, except it's... I guess in Snake you're always moving, right? Yeah. The original game was Tron.
I think that could work too. So to address Billy's point about Agario, so I had said that there are two issues with Agario. One is making your character grow, and the other one is that characters don't intersect. So the mechanic I was thinking about introducing for the second issue is that instead of having characters intersect, it's team-based, and so your team has to work together to like surround a person. And so if another character's completely surrounded by your team on all sides, then they're, I don't know, destroyed, or maybe they're converted to your team.
Yeah, I like that. Yeah, it strikes me looking at the math around the Voronoi diagrams. The first thing that came to mind was Weiqi or Go, which I play a bit of. There's a kind of, it looks like territory, right? Like the dots are like castles, and then you own whatever land is the closest to your castle. So there's a kind of built-in territorial metaphor for the Voronoi diagram, and I wonder, it doesn't really fit with the charming movement of the character, I guess. But I wonder if there's a way for your team to like expand the boundary of your territory by actively doing stuff, but there's also like an underlying, a bit like Splatoon or something, right, where you have sort of some area that's colored your color, and you're taking actions to expand it by cooperating to surround other teams' castles or something.
Oh, that sounds cool. It's like there's an old board game that's like that. It could have just been what you said, but like a simpler kid version that I've played.
I think a difficult challenge will like in brainstorming a couple ideas. I can sort of sense like the problem of what if there's like some equilibrium that everyone's like forced into, like where no one wants to move from where they are because that only like causes them to like lose territory or like depending on what the actual goal is. And so there's got to be some kind of built-in incentive to counteract that, and that could involve like some of the points moving, or they're all moving all the time, or I don't know, and maybe working in teams sort of allows like you to get around these equilibriums.
So geometrically, one interesting feature of these polygons is, well, they have a certain number of sides, right? So maybe if more than half the sides are in contact with sides of a team's players, that square becomes kind of permanently marked, or not permanently, but switches over to be your territory. And so in this way, it would be interesting if the game causes you to reflect on the underlying geometrical kind of logic of the mathematics in these Voronoi diagrams, right? So maybe that's maybe hard because the number of sides required will maybe be changing. So it's perhaps...
I'd like it if there was some no matter what the goal is, if like a if like a strategy always involved like seeing the field and like navigating it like it's kind of like a maze that you want to like find the best path through that will like optimize your chances of getting through, or like the number of points you get, or
Yeah, except in the current algorithm, you don't actually see the full Voronoi diagram, right?
Yeah. But I mean, assuming that's not, we can assume that I could write a new algorithm.
well, I mean, you would just need to see the points, like just in the debug mode. I don't think that you would need to and that's sort of part of it, is like seeing the points and sort of predicting or understanding what it's going to look like and how you can move through them.
So okay, wait. There's a few ideas out there. So what is like the preferred idea? What do we have?
Maybe one thing in common was capture, right? Or doing
Yeah.
something if you surrounded another player. So maybe that's the easy place to start. So if you have two teams, and if figure out whether more than half of the sides, or maybe it's not half, maybe it's just 2 or 3 or some fixed number, that many sides are in contact with another team, then you die. That seems like a common unit of logic to some of these ideas anyway.
Okay, and so it's territory based. So the cells in the diagram become the territory.
It could be used for that, or simply just to have kind of team-based combat. But
Sure, I think that
way,
seems simplest.
Yeah.
I don't suppose we'll finish anything in the next 18 minutes, but
I have faith, Ethan. Go.
Okay. So if we're doing team-based combat, right. So let's suppose this is a character. Right, so they're on the blue team. And these people on the red team. So we need to determine what edges you share with another person and which color team they're on. Right. Okay. So every character is going to need, everybody has to agree on like where these vertices are and where the edges are.
What do you mean agree on?
So the way I'm thinking about it is, okay, so everybody's characters are rendered on the client. So my client renders my character and it renders everybody else's characters. And so if I'm the blue person and I determine that these are my edges and my edges have these sizes and these vertices, and then I go out and calculate the same thing for every other player, I need to know that the other player's edge matches my edge, and the edges are just defined by like positions, by the vertices positions. So so the vertices that I have to match the vertices that I compute for my character with the vertices I compute for another character.
Enter Chickenoid. You could call it Voronoid.
Yeah, that is true. Yeah, I did think about that actually.
I mean, like the simplest thing you could do is probably just like the server does a simulation also, and it makes the decision like you died here. And like whether one client agrees with that at the time and one client doesn't agree with that, like it kind of doesn't matter. I guess to the client that doesn't agree with that, it'll like look a bit weird. But like too bad, I guess.
Yeah, that does make the most sense. So
Like on top of that, then you could like incorporate some rollback like in Chickinoid, but that would just be a straightforward way to solve it.
yeah. Okay, so on the server, first thing we need to do is calculate everybody's edges. And then we have to determine who shares edges. I guess this is like, all right. So the reason I'm having so much trouble thinking about this is that I compute, okay, so the server computes vertices for one player, and then they compute the vertices for another player, and then you and I, we can look at that and go, okay, those are the same vertices. But then the ones that are actually computed might be like they might be off by like some small floating point amount, and so you can't just easily reconcile 2 points as the same point. And so what we need is like some understanding
Can you
that
just
like
store in each region just the like you don't need to know exactly which edge is the one that you're neighboring another cell with. Like you could just have a collection of all the cells that you're neighboring right now.
yeah, okay. So then how would we determine that?
Well, in
Oh, I
the
guess it's known. Sorry, you go.
Well, yeah, like when you create those edges, you derive them from the points that define the cells, right?
Exactly, yeah, because these are like they're bisectors of a known point.
Yeah.
Okay. Yeah, I think that can work. Well, I might as well just start on it. We might not finish it. Yeah, maybe I'll finish at my own time and yeah, share it. Okay. So the code for this is just an absolute mess, but we'll stick this on the server. So what we need to do is run something on Heartbeat. And then we'll also need the Voronoi algorithm. And we're going to need to modify the Voronoi algorithm because when we get back the edges, we also want to know the surrounding edges for which an edge was a bisector of.
You mean the sites?
Yeah, site. Okay. So how do I define an edge? An edge is an array. Okay, edges is an array of edges. What is an edge? An edge is it's a position and a direction. So then we can also include in that a site. Right. Okay. So these initial edges, these are like the very outside box that I use as the original, the first pass of a cell. And so I guess it's not obvious here what the site is. But later on, it is obvious what a site is. So the site later on is, so here's a bisector. The site is going to be the neighbor. Okay. Yeah, okay, this is going to take some thought. I don't think I'll be able to do this right now. I think I might just end it here, unless we want to talk more about game ideas for this.
That's fine with me. It'd be good
All
to
right.
break before MetaUni Dev. But I'm excited to do more of this in the future.
Sorry, I dropped for a second.
I just said I'm excited to do more of this in the future. I think it would also be cool if the teams could, like, under some conditions, they have some ability to manipulate the existing, like the passive just points that are, like the sites that are already there. I don't know if there's like some mechanism by, like, if they surround it in the way that you would surround the opposite team's player to kill them, then like maybe you just capture that region and it like becomes like a sort of like a non-moving cell, but it's like colored with your team's color, so you could like use that in order to like capture members of the other team.
Oh yeah, I see what you mean. Yeah, it was like a wall to pin somebody against.
Yeah, I like that. You could then drive people into tunnels and herd them in directions that are dangerous and stuff. Yeah, that's good.
The danger is always that like there's some, like, out of any of this, like some incredibly dominant strategy arises out of it that just like makes the games way too simple, because you just like do that.
Well, that's what iteration is for, but you have to start somewhere.
Yeah, so but like on that note of like a modification, it could just be like there's like certain points that are like capturable in that sense, and maybe not all of them. Like that could be something to tune.
Oh, like so if a point weren't capturable, then it could act as a wall for either team.
No, it would like, well, it would be just like the other points are at the moment, where they don't create any kind of cell, but there's certain sites that you can like turn into a cell by capturing them.
I understand, yeah. Oh, okay. So you're saying that as a team, you could surround just any cell and not necessarily a player, and turn that into some wall.
Yeah.
Okay. Yeah, I like that. I think Dan is right that the territory idea makes you think about the Voronoi structure, and that is a good goal to have, to expose that, to make people think about it.
Yeah, it's cool. Thanks a lot.